In number theory, there are many interesting different types of numbers. And one of those types of sets of numbers actually is called a Pythagorean triple. Now, we're familiar with the Pythagorean theorem, which allows us to resolve lengths of sides of a right triangle. And this is specific just to a right triangle, as we have learned. That if we have a right triangle and we label two of the sides A and B, and the hypotenuse, which is directly across from the right angle, label that C, then it follows that the square of A plus the square root of B has to equal the square of C. Okay, so a Pythagorean triple is a triple of numbers, that follows this formula. However, since we're dealing with number theory, we are only interested in integer triples A, B, and C. So the question that we might have is, well, if I give you an A and a B, you can always, for the most part, calculate a C, and that value of C may or may not be an integer. What we're asking for is, what are the sets of integers that make this formula true? And that is a lot less trivial, because not every pair of values of A and B will generate an integer for C. And then another question we might have is, well, how many triples like that are there? And you might be familiar with some of those already. Now, any triples that satisfy this formula are integer triples, are called Pythagorean triples. Makes sense. And here are a couple of examples. Well, we've learned about the 3, 4, 5 right triangle. A 3, 4, 5 right triangle. And we can verify that if you take 3 squared plus 4 squared, that's going to give you 5 squared. Let's put a question mark above that equal sign. We have 9 plus 16, which is 25. 5 squared is 25. So you can see that 3, 4, 5 is one such integer triple that exists. Okay, so we know there's at least one, and we can actually kind of construct more of these. Now, it turns out 5, 12, and 13 form another triple. We get 25 plus 144, which is 169, which is the same thing as 13 squared. Then we can also verify that 8, 15, 17 would be one, 28, 45, and 53 would be yet another one. The uncertainty lies in, well, how many are there and how do we come up with these? For the purpose of this concept, let's zoom in a little bit on specific types of Pythagorean triples that will make our process just a little bit easier for now. Let's define something called a primitive Pythagorean triple. So a Pythagorean triple is any triple of numbers that satisfy Pythagorean theorem, that are all integers. And a primitive Pythagorean theorem will be a Pythagorean triple, so a triple of integers that satisfy Pythagorean theorem. And also, A, B, and C have no common factors. So of these that we've generated so far, we know that 3, 4, 5 is a primitive Pythagorean triple, because the 3 and 4 already, those two don't have any common factors. 3 is a prime number, 4 is not a multiple of 3. And so already we know that these are not going to have any common factors. Okay, so all three of them, they do not share any common factor other than 1, of course. 5, 12, and 13, we can also check and verify that. And it is not necessarily the case that all Pythagorean triples will be primitive, but some of them will be. So in the next video, we're going to explore these in a little bit more detail, and here are the questions of interest. Well, how many primitive Pythagorean triples are there? How can we begin searching for them? It's obviously kind of hard to just plug and chug, but we can have a computer help us generate those primitive Pythagorean triples. And then what is the structure of such triples? Maybe if we can get an insight into can A and B both be even? Do they all have to be odd? We can already see what some of them reveal, that it appears that at least one of the values in the triple is even, but we're going to investigate that now in further detail.